Hello students, this is Shakil and this is the second video for part of capacitors, A2 physics, and in this we are looking at discharging a capacitor, its time constant and its potential difference, current, and charge exponential equations. So we have covered some basic stuff about discharging a capacitor in previous video. So today we have to look for the time constant and its equations. So what's the time constant? Time constant is actually a product of resistance and capacitance of a RC circuit. And two ways to define it. The first way is its product of resistance and capacitance in a circuit. And the second way is time taken by capacitor to charge to 63% of its original value, or the time taken for a capacitor to discharge to 37% of its original value. So that is known as time constant. The time constant is represented by Greek letter tau. And of course, as it is time, its unit is second. So what's the importance of time constant? It gives us an easy way to compare the rate of change of current and charge and potential difference. If we look upon the graph, let's say this is the voltage graph and the time graph for a capacitor to discharge. So let's say this is the capacitor that is going to be discharged. This is the negative charge. This is the positive charge. And let's say it's discharging through a resistor R. So if it is discharging, if there is a switch and we have just closed it so that the discharging process starts. So at the start, the voltage between these two plates was maximum. And as time passes, the voltage value keeps on decreasing with the time, and it is decreasing exponentially. So the first thing is that the time constant is actually the time by which the value decreases to 37% of its original value, to 37%. So let's say if it is this, so that is the time. This is the first time constant by which the value decreases to 37%. Let's say here the value is 3.7 volt. So originally it was 10, and then the time taken by the capacitor to discharge to its through 37% of its original potential difference is known as time constant. And then again, when 3.7 is remaining, so then again the time taken by capacitor to charge to its 37% is known as time constant, which is of course like 1 volt. And then again the next. So it's similar to half-life thing. Like in half-life, the time taken by half of unstable nuclei to decay. So time constant is the time taken by a capacitor to discharge to 37% of its original value, and so on. Okay, so now we have to look for the discharge equation. The time constant is used in the exponential decay equations for current, charge, and potential difference. For a capacitor discharging through a resistor, these can be used to determine the amount of current, charge, or potential difference left after a certain amount of time when the capacitor is discharging. It's always important that you should know that how much charge is remaining on the capacitor. And as the previous equation is the decay equation, that it is decaying exponentially, so its equation is of course the exponential equation. Like its equation will be exponential as well. And the general equation is x equal x naught e power minus t over RC. Okay, and at place of x, you can put current, you can put charge, or you can put potential difference. And this RC is the product of resistor and capacitance, and this t is the time in which this original x naught is becoming x. So that is the time. So I is the current, I naught is the initial current before discharge, E is the exponential function, T is time, and RC is the product of resistance and capacitance, which is known as the time constant. So this equation shows the faster the time constant, like if the time constant is faster, the quicker the exponential decay of the current while discharging. Like it will be quickly decaying according to this equation. Also, How big the initial current is, it affects the rate of discharge. If I naught is large, the capacitor will take longer to discharge. Yeah, it's obvious. If I naught is large, it means more charge is stored on the capacitor and it will take longer to discharge. Well, during the capacitor discharge, I naught is always larger than I, of course, because I naught is the initial current and I is the current after certain time, just because the current will always be decreasing. The current at any time is directly proportional to potential difference across the capacitor and charge across the parallel plates. Yeah, this is also important that how current is flowing, the rate of current of flow depends upon the remaining charge on the capacitor. So that's why the same equation for charge and the same equation for the potential difference, the same exponential equation. Okay, then what's the exponential function E? The symbol E represents the exponential constant, a number that is close to 2.718, and on a capacitor, it is shown by EX, and the inverse function of EX is natural log Y, known as natural logarithm function. We have taken that in X-ray and in ultrasound finding intensities as well. So EXY, if EX equals to Y, you take natural log on both sides. So it will be X equal natural log Y, because natural log E is equal to 1. So natural log E equals to 1. So the 0.37 of the definition of the time constant arises as a result of exponential constant. The true definition is uh, the time taken for a capacitor to discharge to 1 over E of its original value. And where 1 over E is 0.3678, and that's almost 0.37, or that's almost, you can say, and this is almost 0.37, or this is almost 37%. So we say that time constant is the time taken for a capacitor to discharge to 37% of its original value. It means it's also the time taken by capacitor to discharge by 63%. So that's the equation. These are the new equations which were added in this current syllabus of 2022. So I hope things are understandable. You just have to focus on these graphs, the time constant, T's RC, and then the use of this equation. It's again quite simple topic, so you should be learning all the terms, especially the graphs, the time constant, and these exponential equations.